Yeah, on part C is talking about find the work done on the student as she walks to a radius, this radius of 0.5. So they are still referring to this radius of the 0.5. So work done on the student. So we are going to consider only the student. In this case, we're talking about find the change in the system. So here we're talking about the system's rotational kinetic energy. But here we're talking about work done on the student. Work is energy. So how can we find that work done on the student? Is we can see if we can find its change in kinetic energy, we can find the work. Work done will be change in kinetic energy of the student. So how can we find the kinetic energy of the student? We just get the kinetic energy of the student. This is final minus the kinetic energy of the student initial. So we have the moment of inertia for the student final, angular velocity of the student final minus 1/2 moment of inertia for the student. So this was supposed to be initial multiplied by the angular velocity of the student initial. So we have moment of inertia for the student has been given as 15 kg per meter squared. Now, what does it mean, 15 kg per meter squared? So for the moment of inertia for the student final, we know that the moment of inertia for the student final is just multiplying the mass times the radius where the student was, and if you get the mass for the student was 60 kg, all right, multiplied by radius to this radius, because final she reached to this radius of 0.5 squared. So if you do 60 multiplied by 0.5 squared, you will find 15. So that's where this 15 is coming from. All right. And then this 4 rads per second, this was the angular velocity final. We calculated it in part in part 1. We calculated this one, the angular velocity final. So that's how come the angular velocity final, we are using this. So minus, what do we have initial? 1/2. Now we have the moment of inertia initial for the student is given as 2.4 times 10 to the power 2 kg meter squared. What does that mean? What does that mean? What it means is that moment of inertia initial for the student is mass. Now here, the initial radius, it was at the edge for the merry-go-round. So it is going to have the radius of the merry-go-round. Remember, radius is squared. So if we have 60 multiplied by our radius of the merry-go-round was 2 squared, because that's where the student is. She was standing on the edge. If this is the merry-go-round, she was standing on that edge. So meaning her radius is the radius of the merry-go-round. So this one, if you compute it, you will find 240, which has been written as 2.4 times 10 to the power 2. All right, this is what we have here. And then the angular speed initial was 2 meters, 2 radians per second. So we are squaring the angular speed. And then when we subtract kinetic energy final minus kinetic energy initial, we get to find this. So there was negative work done on the student, and this is the value that we have found, negative 355. Is that okay on the explanation of how we can find the work done on the student?
Yes.
Okay. I hope I'm not confusing you guys on the final. Your final once it touches on the test should be just on the ease. You don't have to worry too much because your brain will be too much stressed. Just be on the ease. And yeah. Anyway, let's look at a question which I gave you in one of the test papers. I think this was the test paper I gave to everyone. So I don't know if many of you realize that this question was a question on angular momentum, but yeah, it was a question on angular momentum. So let's have Precious to read for us this question. Precious.
The question reads, a ballet dancer is spinning at 3.5 revolutions per second with her arms close to her body, assuming her body to be a cylinder with height of 1.5 meters, a radius of 15 centimeters, and a mass of 55 kg. The inertia is 1 over 2 mr squared. Question 1. What is the angular momentum of the dancer? 2. How much torque is required to slow her to a stop in 5 seconds, assuming she does move her arm from the body?
Okay. So here it was supposed to say she does not. Yeah, there was a slight miss. She does not. So here assuming she does not. Yeah. Yeah. So this is the question, a ballet dancer. I'm sure Precious has been following some ballet dancers. It's a very good dancing practice in our friends, the whites. Yes, a lot of young ladies enjoy or wish to be ballet dancers. And you have to be slim. You have to have only about 55 kg. So, yeah. 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 So, you find that the ballet dancer is spinning. So you find that you have to be spinning 3.5 revolutions per second with her arms close to her body, you know, assuming that she's a cylinder, assuming she's a perfect cylinder, though no one wants to be a perfect cylinder. I'm sure no young lady wants to be a cylinder. Just slim like this, like a cylinder. You have to have a shape that curves like that. Anyway, the idea is let's find the angular momentum of the dancer. So what is the data that we have? The data that we have is the angular velocity initial, she was spinning at 3.5 revolutions per second. And her radius, they're saying with a radius of 15 centimeters. So in meters, it is 1.5 meters. And her mass is 55 kg. Why are we not considering the height? We don't we don't worry about how tall she is. We just worry about so we are saying the height is not important, even if it has been given 1.5 meters. So that is almost above my waist. So she would be very short, but so she would be 1.5 meters tall. But of course, the height is not important in our computation for the angular momentum. And they're like, so we only look at the velocity, the radius, and the mass. So what is the angular momentum of the dancer? Now, the angular momentum of the dancer is, we know that angular momentum is moment of inertia times the angular velocity. So where I, so the I, moment of inertia for the student, the moment of inertia for the student is given as, for the dancer, is given as 1/2 mr squared. But the angular velocity has been given, has to be in rads per second. It was given in revolutions per second. So never do calculations with revolutions per second. Always change them into rads per second. And this is how we change it, 3.5 revolutions per second. We know that 1 revolution is equals to pi rad, like that. And then when we do this computation, we'll be able to change it to our angular velocity in rads per second. So such that when we are computing the moment of inertia, the angular velocity, we'll have 1/2 multiplied by 55 multiplied by the radius squared, which is her moment of inertia. From there, we multiply also the angular velocity, which we found as 3.5 pi rads per second. So 3.5 pi was her angular velocity. Using that formula, we can calculate her angular momentum as this. You get your marks. All right, imagine this was a question in your test. You can get it as easy as that. So are we okay on how we found the angular momentum? Is that your question?
Yeah, something like it. Is the when changing the angular velocity to radians per second, aren't we supposed to multiply by 2 pi rads?
Oh, sorry about that. That's a good observation.
The 3.5 revolutions.
Yes. Yes, that's a good observation. That's a good observation. So yes, this was supposed to be 2 pi rad. So obviously this answer then has a bit of mistake because I used pi rad. So the idea is you have to use 2 pi rads. Yes, 2 pi rads. And this was probably supposed to be 7 pi. All right, 7 pi rads per second. So obviously you have to use your calculator to get the correct answer. So thank you for that correction. So I hope you don't make such mistakes in your test tomorrow. Yeah. Okay, so we are moving on to the second point. If there's no question so far, we can move on to the second point. Second question?
Yes.
Yes.
Awesome. So the second question is talking about find the torque required to stop her in 5 seconds. Torque required to stop her in 5 seconds. So torque, you know that you remember in linear momentum. Linear momentum, if we are applying a force, remember in linear momentum, if we are applying a force at a certain time, we can change the momentum. All right, we can change the momentum. Even in rotational motion, if we apply a torque given a certain time, we can change the momentum, angular momentum. So that is what we have here. They are talking about find the torque required. So remember impulse. This was the formula for impulse. Even here, we are going to use impulse in angular momentum such that the torque multiplied by the change in time will give us a change in velocity. So the change in time, we know it was 5 seconds for her to stop. So how did the momentum change? It changed because at one point she was moving with an angular velocity, which was given as 3.5 rev per second. But then when she stopped, angular velocity became 0. So if her angular velocity changed, meaning her momentum changed, so therefore we know that we can compute torque by the change in that momentum over the time of the impact, or the time of the torque, the application of the torque. So we know that there is angular momentum final minus angular momentum initial. Angular momentum final, we have the moment of inertia, 1/2 mass times radius squared. Final, she stopped. So we have a velocity of 0. But initially, we have also here the moment of inertia times the radius, but we realized that she was moving at that angular velocity of 3.5. Now, of course, we say that since we're supposed to use 2 pi rad to convert angular velocity in revs per second to convert it to rads per second. So this was supposed to be 7 pi rad when we use, in fact, yeah, it was supposed to be 7 pi rad. So there was supposed to be a 7 pi rad here. So I would like you to go and use the calculator properly so that you get the actual answer. So the idea is we can use the idea of impulse. We know that its momentum changed because she stopped. And then when she stops, we know that the angular velocity final is 0, not so? Yeah, that's what happens when you stop. So when we compute the change in momentum over the time that it took, 5 seconds, we're able to find the torque. Like I said, you need to, again, confirm with this value because I used a different number here. So you need to confirm with this value and get the correct finding. And then actually this torque was supposed to be a negative because here we have a 0. The whole term here will become a 0. Will become a 0 minus this number. So we'll have a torque which is negative. And then this is how we're supposed to compute this question using the concept of angular momentum. I guess I was thinking homework, but anyway, I think the homework is, yeah, the homework is just for you guys to go and continue looking at papers and don't stress too much. Tests in NS are not usually very difficult. So just relax, you'll be all right. Otherwise, you have any question?